Couple announcements before we get started with instructions. I'm ready. You know, when I get evaluations, sometimes students, especially because of my leg, they criticize me for being late to class. All right, that's fair. But what about the amount of time that we waste just not listening to me? And I have to ask you 50 times to hush Winkies, hush your, hush your mouth. All right, so let's go. Couple things. There's our outline for today. We're going to do some more combo box experiments, measurements with current today. It looked like Bruce Wayne out there in the corner, some guy that looked like young Bruce Wayne. I'm going to post your iClicker scores from exam 1. I've had them for like over a week, and it's to grade them with justice, giving partial credit and stuff is a little bit of work. I got it done like over a week ago, and I keep forgetting to put them up, but I'm going to put them up today during off hours. Second comment, off hours 12:30 to 1:30. So if you want to come and study or talk about the weather or anything in between, welcome. If you want to bring some lunch, welcome. But that's 12:30 to 1:30. That looks like a nice cup of coffee, Matt. Is that deliberate? I mean, did you time it? Okay, everybody's in there now. Go in. You didn't? You didn't do that? So it's dramatic, the coffee entrance, the dramatic coffee entrance. All right, let's do some iClicker questions. And we all know what the iClicker questions are going to contain, but before we do the electric field workout, at which you guys are getting pretty awesome, which is what I want, I have another kind of bookkeeping. Now, this one's not going to be for a score. Well, I'll give you a point for answering this. Basically, I need your username in Instagram. So, and this is alphanumeric, so go ahead and type in. Because some of the names that I noticed joining my list, I'm not really sure they're in this class because they featured unusual photos of themselves. So I want to know. And then what I'm going to do is I'm going to retain your username and then ditch the rest of them. And then make the feed private again. Because I don't want some maniac joining my Instagram and talk to me about homework of stuff. They're not even in this class. What if I wanted to give them extra homework? Through Instagram. You laugh, but it happens. Students, every semester, 3 or 4 times, students ask for more homework. What? Do I have a what? I thought it was public. Raise your hand if I added you to my feed successfully. So I did a bunch of them Monday afternoon and then yesterday. But it's just what to subscribe to it, what do you do? Do you ask to follow? Okay. Right, so I'll be picking people whose names are on this data set. Okay.
You approve my request.
Very good. Yeah, I figured yours, I figured out like a few people's, because it was their name or pretty close to their name. But some of them are like, if I were to use that handle in class, I would instantaneously get in trouble. All right, 30 seconds starting now. 20 seconds. Can you guys do a count? 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right. Let's. I'm not gonna. I'm not gonna go through this list because some of these are a little dubious, but that's all right. Actually, some of these have your guys' names, so that's good. But a lot of them, yeah, see this one I couldn't. So okay, some of you say no. That's all right if you don't want to join it. Okay, so those look all right. I'll try that. We'll try to do it one more time on Friday. Give everybody rounded up. Okay, next question. Short answer again, type in letter A, B, C, D, E, or F. Now this one's a little bit different because the proton is way up here on the y-axis. And I'm using the same scale as before. Point S is down here, 2, 2, but the proton is way up here. But you can handle it. Twenty seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, how many? Okay. All right, the rest of you guys that just got here, make sure you get your clickers out. Yeah, correct answer was D. Most of you got it, 96%. And let me reinforce something, you guys. When you're doing a problem, we haven't even done the test problem yet, because that's putting together a net electric field from two different source charges. We've only been working with one proton each week, but we're going probably Friday I'll start using a proton and a proton, or a proton and an electron, or an electron and an electron, and see how you guys handle it. But my comment to you is, figuring this stuff out, as complicated of a set of charges as you have, it's no more complicated than this three-step process that we're doing, as many times as you need to do it. So for each source charge, you figure out the field. First of all, figure out the basic direction. And what that tells you is you're going to have a negative y component when you try to figure out, do the trig for the y component. And you're going to have a positive x component, basic trig. Now, some of you, it's been a while since you had trig class, okay? But we're, trying to work it through. And Matt, you have a strategically placed big head, because I'm trying to see what Melanie's munching on over there. It looks like nuggets or something from Chick-fil-A. No, that's not Chick-fil-A. Anyway, so my comment to you is, remember to It's a series of fairly simple tasks, but but the hard part is keeping them all organized mentally in your head or organized on your paper. You know, that's equally important. All right, let's go to the next question. Let me click out of there. All right, calculate the magnitude of the electric field at point S from this proton at 0, 7. There's the a typical field vector in red. All right, let me get my dot cam up here. Which I know it's working, so. Okay, that should be pretty good. You guys can stroll around if you want. What is this? No coffee for Dr. B Day? And no coffee for Ken. Now that's a double offense. That's offsetting penalties. See? Even though I don't drink coffee anymore. See, now look at Joel over there. He's got 2 things of coffee. Oh, oh, just one. Nothing. Well, Joel's got, but that's not even coffee. What is it, a protein shake? And you have one too? I get those at Walmart, yeah. Is that where you got that? Target? Yeah. I have a bunch of those in my office. Yeah, for emergency supplies. Yeah, it's good protein. It's easy to carry around. It doesn't go bad. Where's Daniel? It's another guy getting in late. Logan Jones, where are you today? Oh, okay. Well, your picture is way different. I gotta memorize your face. Seth Lucas, are you here today? Okay. Shakira McDuffus. Shakira. I was using the past tense. From 2 sources. Well, it was. We're drilling them on this. They did so poorly, they need extra drill on this. Good idea. All right. Christopher. Better late than never. 2 minutes. It shouldn't take this long. Yeah, you never know what's going to happen. But there's always a reason for everything that I do in this class. I have to read the book, decide what is important enough to cover in class, and reject the stuff that is nice but can't. Yeah, because I can't lecture on every sentence in every paragraph in every page of the book. So I have to make decisions. So whatever you see in lecture is important. Think of it that way. So that's, you know what, I'm having a hard time with my astronomy, my online astronomy students. They, there's a lot of, like last night I was talking to a student that's an accounting major. So I guess her classes are all like ultra organized, like accountants have to be, with book chapters and readings and everything timed out and stuff. And, without having to, so that particular student that's my eraser. Yeah. Put it on the, put it down there, slowly back away. Okay. Yeah, you got to use those on Scantrons but she was, she was, because for me, it's all about lecture. If it's not in lecture, it's not going to be on the test, no how. Some stuff that's in lecture might not be on the test, but if it's not in lecture, it ain't going to be on the test for sure. So, and that's the same principle, you can't give a 4-hour midterm until you get to, have you had that in grad school?
Dude, I've had a 3.5 hour midterm like last semester.
Dude.
Geometric optics, dude. That class is taught like a grad child. He kills us.
Yeah, I had an optics class that
What
was,
section time for the like test?
yeah, common
Regular
hour.
tests are 2.5 hours.
Yeah,
Final like 3.5.
yeah, that's insanity.
Finals are about
Yeah, most of my my first 2 years taking classes in grad school, we would have evening exams, and which is bad for me because I start running out of gas at about 7, and by 8 o'clock, because I'm a morning person, by 8 o'clock my mental efficiency is, plunging down the exponential curve, so to speak. But a lot of pressure too. Okay, 10 seconds. 10, 9, 8, 7, 6, 5, 4. You got it? 3, 2, 1. Hurry up. 0 point whatever. All right, here we go. 80 students. Good. Oh my goodness. You guys deserve a round of applause. 90%. So how come it takes like 9 minutes? Just curious. And anyway, that's good. Glad for you guys. Um, so there's your answer, 0.497. All right, Xcomponent. Question 3 for today. This is the calculator of destiny. People that have one.
Yeah, I have like 5 different.
Tell me about it.
I think I have two.
2 minutes. Yeah, this should not take more than that. One minute. Very nice. You know, what's nice is to be up here and look out and see the students working with each other, you know, on different calculations and stuff, which is exactly what we're supposed to be doing in this class. 20 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Jordan Legister, thanks for helping out your group mates. Destiny James, got it? Hurry up. We're overtime here. We're burning daylight. Got it? All right, 80 students. Um, all right. Shh, 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 shh. All right, let's take a look at these answers. All right. Now the correct answer is 0.185. And here's your breakdown. 65% of you got it. That's good. Now 0.184, that's a little bit of round off problems there. I don't know about this one or this one or this one. Zero point 0.4. Oh, you know what that might be? That's the Y component maybe. You did the wrong trig. Is that what it is? Is that what? Right, it should be. Well, let's see if we got a negative 461 here. 469, 496, 582. What was the magnitude of the 497? You can't have something. Hey, you guys, now look at this. Look at these these two answers here. 0.586 and 0.652. You can't have an X component or a Y component that's bigger than your hypotenuse. That's no good. Right? So that if you come up with that for a component calculation, go back and check again. Right? That should tip you off. Now these ones down here are off. 21 and 11. Let's see what else we got here. 3.6, 338, and 9. Nah. All right. So that's a few of you down here in the you know, left field answers here. Um, And this one is the Y component. So that's not. Now on a test, I would give partial credit to 0.164. But I wouldn't give jack to 0.461. You got to know your, you got to know your trig and your directions. Okay, so that one's clearly out. But let me say this: on a test, if by some miracle I was to give you a problem like this on a test in the future, Brandon, it's a big if. But if I was to give you, I'd probably do both, ask you for both components, because then you'd be able to combine it with the components of another electric field component or constituent field, and then get a net electric field. All right. Now I want to make a couple more comments about this. These components are important. As I just said, that is how you assemble the net electric field in the x direction and the net electric field in the y direction. You have to have components for every constituent field vector. Now we've only got one constituent field vector, so this is all we got in this problem. But if I give you 4 or 5 different point charges, source charges, and one field point, you might have 10 different components. Now, if your source charge is immediately above or below the field point, then you don't have any X components. So that one's easy. If your field point is directly to the left or right of a source charge, then you don't have any Y components. It's just a left or a right. So those are easy. But like this, every one that I've been doing with you since the test has been slanted in some tilt angle. All right. And I've made them a little bit cinchy because I'm using integers of nanometers for the dimensions of the diagram. But I might not do that if Brandon, if by some crazy confluence of the stars and my mental state, if I were to give a problem like this on a future exam, you'd want to be able to hack all this stuff apart and do it quickly. All right. Now, before we do any more clicking, let me get my thing over here. I want to talk about the 4 voltage measurements from Monday. So go into your notes from Monday if you have them. Let me get a show of hands. Raise your hand if you use an actual paper notebook for taking notes in this class. That's a good. Nobody at this table does. Oh, you do? No, iPad. No, I'm gonna. How many people use an iPad or a stinky Windows, whatever? Okay, still a minority. All right, so page back to your voltage measurements, and let's kind of review. Now, what I did, if you looked at Instagram, you saw the scoreboard for, I think it was question 7, which was one of the voltage measurements that we did. All right, now I'm going to go through the 4 voltage measurements in terms of this diagram. All right, so there's my fluke. And this schematic is basically the diagram, the schematic for what we were doing. All right, we had that little green base with the posts, but that's kind of abstracted out of a schematic. It's basic. And usually the light bulb is replaced with a squiggly for a resistor. Anyways, so the 4 voltage measurements, the first one we did was the battery across the terminals. Now make a sketch of this circuit and the fluke, kind of drawing a rectangle for the fluke, and then draw in your 2 probes. Now the black is the common, and the red is the voltage side of the meter. All right, now what we did was terminal to terminal. And that gives us the voltage across the battery, across the terminals of the battery. All right. And here's the average value, 1.58 volts. Now what I did was I took the absolute value of everybody's reading, including some readings that were out in left field, but I just included them. And as we get, we might do this measurement again at the end of the semester when you guys have more skills. I might get a little tighter. I didn't compute a stand. I should have done a standard deviation to get a little plus or minus action on this. But anyways, there's our average for the battery voltage, the nominal voltage of the battery. Actually, the nominal voltage is 1.5. The measured voltage is 1.58 on average. Right now, the next one that we did, go ahead and draw another sketch of the schematic with the fluke. The positive terminal up to the bulb. So that would look like this. All right. From the common up to the bulb and the red voltage up to the positive terminal. Now we did that one. That was our second measurement, and that was the biggest one. Average. Oh no. That was our second measurement, but it was not the biggest. But it was an average of 0.28. Now, what does that tell you about that part of the circuit? Think about what that tells you. Because the schematic diagrams we use a schematic to represent zero voltage. So that thing, schematically is not supposed to have any voltage, but we measured it because it's a real wire, one of those yellow alligator clip leads. What does that mean to have a potential drop of 0.28 volts? Think. You have a patient in the ER, and your measurement is 0.28 volts between his defibrillator, his pacemaker, and ground. What does that tell you? If there's a voltage drop, what is happening? What happens when you have a voltage drop? What's that? It's a difference in potential of 0.28 volts. That's right. But what's happening in the circuit? What? What's being used? The circuit? Right. The energies, that's it. Thank you, Peter. The energy is, so make a note, the energy there is being dissipated, we would say, somewhere this much, or fundamental charge times it. So 0.28 electron volts per charge carrier between the positive terminal and the bottom of the light bulb. But that's just a wire. So that tells you that the wire actually has some resistance. It's not a superconductor. And that's true for all wires. Right now, our schematic doesn't allow for that, but our actual measurements, yes. All right, let's do the next measurement. All right, this one's from across the bulb. So that one looks like this. Kind of make another sketch from the black common jack up to the other end of the bulb, and then from the red common, or from the red voltage jack to the bottom of the bulb. Now the average for this one, this is the big one, 1.03 volts. All right, so now what does that tell you compared to measurement number 2? What's that? Greater potential difference. And that means what? Comparing the wire and the battery. See, because I could torture your minds with a multiple choice question about this. Cassandra, go ahead. Less resistance, but more work is being done. Half of that is correct. We don't know what the resistance of the bulb is. You can look it up, I'm sure. But definitely more work is being done. Every electron blazing through there is doing almost 4 times as much work at the bulb than it is getting across that wire. All right, let's keep going. The last of the individual measurements was from the bulb over to the negative terminal of the battery. All right, so that's this one. All right. So from the common jack down to the negative terminal, and from the red voltage jack up to the other side of the bulb. All right. Now the average for this one was 0.51. Now let me ask you this: how is it that number 2 and number 4 are significantly? Those are different. Those are different measurements. I wonder why that is. Anybody have a notion? What do you think? What is your name again? Paul. Nope, there's not different charges. The same charges that go out of the battery are going through the circuit and back into the negative end of the battery. All right, so it's not different charges. Okay, I'll give you one possible explanation. It might be a lot of mismeasurement at the negative terminal. Okay. In fact, there's probably in all these averages, there's a lot of mismeasurement, but some of it's high and some of it's low. So these are going to be these are what we call the central figure, the central average. All right. But this one is probably a little bit more susceptible to mismeasurement. That's my guess. But it might be, because the wires all look the same except for the color. Now, I asked you to calculate the sum of number 2, number 3, and number 4, and then compare that to number 1. And what you guys, what the average gap is 0.24 volts between what you drop on the 2 wires and the battery. That's the sum of 2, 3, and 4, right? And what the battery actually says, right? So if you look at what you drop on the 2 lengths of wire and the bulb, it's actually a little bit greater than 1.58, right? So that's a problem, all right? And I asked you, why is it that they don't match? And the reason for that lack of matching is the fact that the battery itself has something called internal resistance. Now you can read about that in chapter 21.2. Matter of fact, here it is right here. Chapter 21.2, electromotive force, terminal voltage. Now, when you look at that stuff, which is going to be your homework assignment over the weekend. Yeah, you can. The battery is basically 2 different kinds of metal plates with some kind of ionic solution in kind of a pasty material in between them. So they're in electrical contact, but it's not a superconductor. And so there's a little bit of internal resistance. And that is basically why the sum of the voltage drops you get at your two wires and your device might not add up to the marked voltage on the battery or your measured voltage at the battery. All right. So now, so go ahead and make a note of that internal resistance, and that's your clue for your prompt for reading up to chapter 21.2 over the weekend. And that's my prompt for annotating stuff up to chapter 21.2 over the weekend. Now, what we're going to do next is measure some currents with the fluke. Now, we've already done voltage. That's part one of this outline. And what we're going to do now is measure current. Now, go ahead and make another picture. And hopefully you're using pencil, because the way that you measure current is you remove a segment of the circuit. Now watch the line segment between the positive plate and the light bulb. Now I animated this really carefully. All right, you break the circuit, like if wherever it is that you want to measure, and then you wire your device in to replace that break. So here's my replacement. All right, that device now, we've set it on common and either amps or milliamps, and we're going to do amps today for safety. Okay, and now this device is in series, so all the current that leaves the battery at the positive side goes through the meter, and that's how we measure the meter, or the current at the meter. And then it goes through the light bulb. So when we do this, we're going to see the light bulb light up. The fluke, this circuit of the fluke, is going to have a very, 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 very low resistance, because you don't want those electrons to do any work getting through the fluke, as little as you can. All right. So we don't want a big resistance there. We want a really small resistance, and maybe get just a little bit of work out of it, just enough to light up the meter, and most of it going, and not wasting any of the current. All right. So basically what we do is we put the meter in as part of the circuit, another circuit device. Instead of measuring across, like when we were doing voltages, we basically had a parallel path for the device. This one, it's in the line. It's in line. It's in series. So that's how we measure it. Now, what we're going to do, Kendra and Andrew are going to hand out meters and combo boxes. So put down your nuggets and your lattes and stuff, and come on up here. By the way, whoever brings food in here, you're violating this admonition up here. And unfortunately, I bring stuff in too, so I'm not going to arrest anybody. Come on up and get one for each group of three. Let's go. Yeah, you can do four. Guys versus girls. See which ones survive. All right, now let me. Okay, we're going to make some measurements here. I'm going to pause the YouTube. Okay, so we've done our one bulb current measurements, and next time we're gonna do some fancier circuits. This is just the basics, just so you guys get to know how to, the basic stuff of measuring current, measuring voltage. All right. Now, let's make a record of your current measurements. Okay, so take a second to type in. Now, this is from the negative end of your battery to the negative side of the bulb. That was our first one. Oh, yeah, type in the groups. Actually, hey, you guys, hold on a second. Hold on. All right, let's do the next one from the positive side of the battery to the positive side of the bulb. Go ahead and type this in as a positive number. So 0. Something something. And just do it real quick. See what they got over there on the board. It's a bunch of that's Ohm's law for a bunch of batteries and a resistance. 10 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Come on, get your number in there. What do you? This is burning my grits. All right. Now, all right, here's the results chart over here. And you can see we're in the same ballpark. All right, except I don't know about these ones down here, 0.1 and 0.09. Those might be typos, but most people are up in this other area. Now, let's hit the refresh key, and I'm going to ask you a multiple choice question now. Okay. And it's a simple. Do your two current measurements agree exactly? And this is kind of this schematic is a little bit like what we had. Our fluke between point B and C. Oh. All right, go ahead and get your answer in. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Well, this is interesting. This is better than yesterday. 66% of you, it agrees exactly. I dare say that the other 34% are probably pretty close. Raise your hand if it's pretty close, within about 1/100 of an amp. Well, wait a minute. Raise your hand if either it's exact or pretty close. All right, that's pretty good. All right, let me go back over here. Now let's take a look at this circuit for just a minute. Our first measurement was basically from D in this circuit to the small plate in the battery. This is a diagram from the textbook. All right. No, actually, it's from D up to the top end of the internal resistance, the right end of the internal resistance, the little R down there. Okay, that was our. So we rubbed out. So in terms of the circuit, the ammeter the fluke is And our first measurement was over here. All right. In our second measurement, the fluke is over here between B and C. All right. So this one, our second. And C and D are the two. So make a note. C and D are the two posts of the light bulb platform. And then B is the positive terminal. And then down here at the other end of the internal resistance, you know, if it was me making a diagram, I would put in a point here and call it point F, because you can't use letter lowercase e or capital E on a schematic diagram. It's too ambiguous. So I put a little dot and an F there, and then between F and D is where our first measurement was. We wired the ammeter in between there, the flute. All right. Now remember, chapter 21.2 is where I pointed you to understand the internal resistance. So what I want you to do for homework, we're going to dismiss a little bit early. We went really nicely today, so we have a little extra time to dismiss early. So I want you to read ahead into chapter 21.2. And Friday, we're going to have a clicking extravaganza. We might have up to 20 clicker questions. So do not miss class on Friday.